My name is Fuhry, and I'm from SAP Security Research. Today, I will present you how to build an efficient, encrypted, compressed in-memory database. The focus here is really on the encryption part, because most of you might know that there are efficient compressed in-memory databases out there. Now, the disclaimer, all of you also saw that, but please note, this is especially valid for this talk, because I'm from security research. We do what will be or can be in the product in the future, but it is not. You cannot buy what I present you today. You can help me make this possible. I will come to that in the end, but it's not in the product now. Okay, the agenda, I will start with a short motivation of the topic. I will give you the needed background, especially about the technology called Intel SGX. And then I will give you details about databases, like what is an in-memory database, what is a column orientation, what is dictionary basing or dictionary encoding. Then I will come to the main topic, which we call the solution EncDBDB at the moment. And this is really an encrypted in-memory column-oriented dictionary-based database. There I will start with the main building block, which we call encrypted dictionary first, and then I will explain you how we use this main building block to then generate a whole database management system. Afterwards, I will give you some evaluation results and end with the key takeaways. Okay, to the motivation. We have here a customer, and this customer has its database on-premise. The customer, you heard of the cloud, all the benefit it brings, and now he wants to export its database to the cloud. However, the cloud doesn't only have benefits, it also has problems, and we concentrate on, let's say, security problems here. First, there might be internal and external attackers. For example, administrators that are just a little bit too curious, or hackers that try to steal your data. The cloud provider could think, oh, I now have all this nice data, let's put some analyzers on that and sell the data, or sell the data directly. The customer obviously does not want that. Furthermore, all database management systems and operating systems can have vulnerabilities that leak the sensitive data of the customer. And lastly, by now, also governments learned, oh, there is now this one single point of data. Let's just go there and access the data. The customer doesn't want that either. So our idea is to encrypt the database. All data in the database should be encrypted at all time. To make it explicit, we don't talk about at-rest encryption here. This is done by HANA. Today, many databases do that. We also don't talk about in-transit encryption. Many databases do that. We talk about encrypted data processing. So the queries in the database are processed on encrypted data. And here also the customer sends protected database queries now, because if he sends plaintext queries, the server would also learn that. And by doing encrypting the database, having protected database requests, we hinder all of the problems that I described before. Okay, to the background. And first to Intel SGX. SGX per se is an extension to the CPU instructions that was introduced with the Skylake generation. The Skylake generation is from approximately 2015. Since then, all mobile and desktop and low-level server CPUs have Intel SGX in them. So for all of you in the room, most of you have Intel CPUs, you have Intel SGX. You only don't know it. What is the idea of it? The idea is to execute isolated parts of a software. This means you can execute software in an untrusted environment, but it's still protected. And I will talk about how this is done in the next couple of slides. If you develop a software for Intel SGX, you have to separate it into a trusted part, that's called enclave, and an untrusted part. And we see this in this picture here. And I will just go quickly through the flow of such a split program. Your program always has to start in the untrusted part of the application. It does whatever it wants, and at some point it will create the enclave, the trusted part. It does again whatever it wants, and at some point it calls a trusted functionality. You see here with those little squares, those are predefined functions. You have to predefine the functions that are callable in the enclave. You cannot jump at a random point. You can only call what you defined before. The enclave executes whatever it wants again, at some point returns. And this loop can repeat over and over again with different functionalities. At some point, the untrusted part just dies, and the enclave also dies. The important thing here now is we have to privilege system code, the operating system, the virtual machine monitor, or the BIOS, and none of them can access the enclave. None. So you really can run specific functionality in an untrusted environment. If you don't trust, for example, SAP and rerun Intel SGX in our data centers, we can run your code without you trusting us or without us having access to it. And one design principle I follow with my research, and you should also, if you ever consider using SGX, keep the enclave as small as possible. Your attack surface now is the enclave. But if your enclave leaks data via any means, it will get leaked, right? So keep it small. Don't have the idea, just take a complete application, put it in there. You might have problems with that. One key factor how enclaves are protected, so the code in there is protected, is all enclaves have a dedicated part of the main memory. And this dedicated part of the main memory cannot be read or written by any other software. Even another enclave cannot access the main memory pages of the enclave that created them initially. And even if it somehow is possible, if there is a software problem or whatever, the data in this dedicated part is encrypted. So you see this here. So the system memory, the main memory, it only contains encrypted data. You can snoop, but it doesn't really help. You get encrypted data. On the bus to the CPU, also encrypted data. Snoop, but doesn't help. Only in the CPU package, let's say here, like directly at the edge of the CPU, your data is decrypted. And then for the CPU, the data is plain text. So the cache has plain text data, and your program, it thinks it has plain text data. Another important feature of Intel SGX that we use later, as you will see, is so-called remote attestation. The idea of remote attestation is that an enclave can prove that it's running on a genuine Intel SGX processor and the code is as expected. I will just repeat this with a short example. Let's say I'm SAP. We have a customer of SAP and we have a partner of SAP that developed some enclave. This partner developed the enclave and calculated the hash of the enclave. It then gives the hash to the customer. And the enclave is then given to us, to SAP. And we provision it in our data centers or at any other hyperscaler. Doesn't really matter. And then we as SAP can prove the customer that the code is what he expected. So what was promised from the partner that developed the enclave in the first place. And we can prove that it's running on Intel SGX CPU or SGX-enabled CPU. And the process to do that on a high level is the following. When we load the enclave in our data center or we really start the enclave then, we measure it. Every page that's loaded in is hashed. It's hashed, 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 and we have one final hash that's the identity of the enclave. The hardware then creates a report out of that hash. It's a so-called, it's a signed measurement. Measurement is just another term for hashing in this SGX environment. The hardware does the report, and then another, let's say, software component transforms the report to a quote. The quote again has a signature, but that's now from Intel. And with that quote, we can give it now in our scenario to the customer. The customer takes the quote, goes to Intel and says, is this a valid signature? Intel says yes. Customer says, okay, great. And then compares the measurement in there. Is it the measurement he got before from the developer, from our partner? Says yes, great. Then we have done what's promised at the beginning of the slide. Another important feature of remote attestation is it can be used to establish an authenticated channel. This means a channel where every message is encrypted, integrity protected, and has defense against man-in-the-middle attacks. And this authenticated channel then can be used to transfer secrets. So the customer can transfer secrets directly into the enclave. In our scenario, in the enclave hosted at SAP, without SAP having access at any point. And we see later how we use that in our case. One last word or slide about Intel SGX, the restrictions. First, you have to trust Intel. You have to trust that they really have implemented on a microcode level what was promised. I always say you have to trust Intel anyhow. Your CPU is basically God on your machine, so I don't know if that's a problem. Furthermore, I/O is not possible because I/O is an operating system functionality and the operating system is not trusted. So you can do I/O, but with the untrusted part. So you have to make sure that this I/O is somehow made trustworthy via encryption or via other means. Third, Intel SGX does not protect you against side channel leakages. For example, if your processing has timing problems, so if sensitive data is leaked by timing, you have a problem. You have to care about that during your programming. And finally, I talked about this dedicated memory. And at the moment, at the current version of SGX, you only have 96 megabyte that you can use as this dedicated memory. And this is for all enclaves running on the CPU. They even have to share this. But please stay with me still. Don't go away. Say, OK, I cannot do a database with 96 megabyte, right? Doesn't make any sense. We by far don't need those 96 megabyte. We can support really large databases with our solution. Yeah, this is just a minor detail. Linux supports paging to have a little bit more dedicated memory, but this has a severe impact on performance. OK, let's come to databases. And we start with what is an in-memory database and what storage concepts are there. I guess most of you know that. But in-memory databases more or less means your primary data persistence is in main memory. So every processing happens in main memory. The data is loaded from disk in main memory and only processed there. We still need a disk, but only for data consistency, for logging and data recovery and so on. To the storage. A database obviously consists of multiple tables. And a table is a 2D data structure consisting of rows and columns. However, we want to store it in main memory on disk, and those are 1D data structures. So we somehow have to convert those 2D tables to 1D structures. And there are mainly two alternatives to do that. The first is row orientation, which means we have here a row, alpha 20 Germany, and we store this row first, then the second row, and so on. And the second possibility I want to use here is column orientation. We store all names first, then all ages, then all countries. And as obvious from the title of my talk, we concentrate on column orientation here. And I want to shortly show you the features of column orientation. And I start with the main downside. We have an overhead for tuple reconstruction. What does this mean? This means tuple reconstruction means I want to get all data that belong to one row or one tuple. For example, I want all values that belong to alpha. If I do that, it's alpha 20 in Germany. And I have to jump now in my main memory. And this takes time. On the other hand, this is the huge advantage if you have operations on many rows, but only on a few columns. For example, calculate the average of all ages. That's pretty fast now, because they're consecutively stored in main memory. And those types of operations, you have them in OLAP workloads, for example, in data warehousing scenarios. And lastly, dictionary encoding is possible with column orientation. And what dictionary encoding is what I will talk next about. You see here just one column of last names. And I will firstly talk about the setup of such dictionary encoding. We split the column in two data structures, and the first is the so-called dictionary. We see that on the top right, and it contains every value once that's contained in the column. So look here, Ajax 1, 2, 3 times, but Ajax is only once in the dictionary. And the second data structure is the so-called attribute vector. And I will show you with a small example how that's built. Let's look at the last names Miller. Look to the dictionary, and we see Miller is stored here, and it's stored at the value ID 2. Go to the attribute vector, and we see at the points where Miller was before, at the so-called record ID 1, here 1, we have now the 2. So instead of storing strings all over again, we only now store the value IDs, which are the indices of the dictionary. If we now want to perform a search, it's a two-step process. First, we always perform a dictionary search. So again, to our example, I want every value that's Miller. I first go to the dictionary, search for Miller, go through it, go to Miller. Oh yeah, okay, Miller's at value ID 2. Then I perform an attribute vector search. I again scan through the attribute vector and see, oh, 2 is here, great, record ID 1 is the result, 2, record ID 5 is the result. That's how a search is done if you use dictionary encoding. And the advantages of dictionary encoding are, most and foremost, data deduplication and data compression. Here, instead of storing Miller twice, we only have to store it once. But in an actual column, Miller might there millions of times, and you only have to store it once. Secondly, string comparisons become integer comparisons. And this is especially true for the attribute vector. We have the value ID 2, and then only have to do integer comparisons here, which is much faster than string comparisons. It might even be bits instead of integers. That depends on your implementation. Okay. A short recap of what we've learned about databases. We learned what is an in-memory database, what is column-oriented storage, and what is dictionary encoding. And maybe many of you know that. Those are the features of HANA. So my research really is dedicated to a HANA-like database management system. And now let's come to the main part, EncDBDB. As told before at the beginning, I will start with the main building block that we use to do it, and only then explain you how we use that building block to generate a whole database management system. This building block, we called it Encrypted Dictionary. And those encrypted dictionaries, I will present you 9. And the 9 encrypted dictionaries are separated or categorized in 2 dimensions. First, the so-called order options. You will learn in a second what that means. And repetition options, which we will also discuss. The first order option is sorted. The first repetition option is frequency revealing. And the result of that combination, we call it ED1, for Encrypted Dictionary 1. For this encrypted dictionary, you already see an example on the right. And the important thing is here, you have the dictionary, and every value in the dictionary is encrypted. And I said it's sorted, so this is the order option sorted. So all the plain text values underlying, they are sorted lexicographically. HX, Lee, Miller, Smith, White, right? Sorted dictionary. Now I want shortly to explain why this is frequency revealing. And for that, just let's look at the yellow cells and attribute vector. The cloud provider or an attacker, he doesn't know that this is an encrypted AJAX because it's encrypted. But he sees here 0, 0, 0, so he knows it's there 3 times. So the frequency is revealed. And this might leak more information that you want. In some cases, that depends on the case. Yeah, and for example, the other example is Smith here. It's only there once, which is also leaked. Okay, let's come to the second order option that we called wrapped. Here, the dictionary is still sorted. HX, Lee, Miller, Smith, White. But it's, so we call it wrapped, right? At this position. You can also say it was shifted by 2. So we have the array and we shifted it by 2, wrapped it around. This is the result. And I will just quickly toggle back and forth. Please look at the attribute vector, and that's especially the colors, the blue and yellow colors or orange colors. The orange and blue stays exactly at the same position. Only the numbers in there changes. And the numbers obviously change because the dictionary is different. So the value IDs are different, so the numbers change. But the record IDs of the results, they have to be the same because you want to be able to do tuple reconstruction in the end. And you cannot do that if you change the record IDs. To the third order option, and we call this unsorted, or you can call it random. And here in the dictionary, we just have a random order. The result here is, again, the numbers in attribute vector changes, but the positions, the record IDs do not. Okay, let's come to the second repetition option called frequency smoothing. I told you before the problem was that an attacker can count the equal values in the attribute vector. Now we added to the dictionary we just added a duplicate of AJAX. AJAX is now there twice. Please note, they are encrypted with probabilistic encryption. This means the ciphertexts are different even if the underlying plain texts are different. So an attacker looks at the dictionary, he sees 2 encrypted values, and he has no idea that those values, the underlying plain text values, are equal. But look at the attribute vector now. We have 2 1s and 1 0. So we smooth the frequency. That's why the name. I won't go into detail about the wrapped and unsorted versions here, ED5 and 6, because it's obvious what's happened, right? We wrap the dictionary or we randomize the dictionary. To the third repetition option, and we call this frequency hiding. Here we add to the dictionary every value as often as it was in the original column. Remember, HX was there 3 times. So it's now 3 times in the dictionary. Obviously, you lose the main advantage of dictionary encoding, your data compression. That's totally clear. However, if you look at the attribute vector now, and all of the HXs, 0, 1, and 2, the attacker doesn't learn that now. The frequency is hidden. Again, don't go into details about 8 and 9. What's important about the 9 encrypted dictionaries here? They provide you or customers different trade-offs, especially regarding security, how much order or frequency is leaked. They give you a trade-off regarding performance. Obviously, it costs a little bit to have additional security, and we will learn in the end how much in our evaluation. And third, you have a trade-off in storage efficiency, because if you add multiple copies to a dictionary, you have to store more. That's clear. In the rest of this talk, I only will talk about ED1, 2, and 3. We don't have time to talk about the rest, you can view the details or read about the details in a paper that will be published soon, hopefully. Yeah. And let's now get into details of ED1 and how a search is performed there. We have, again, the same example column, the same example dictionary at the bottom, and we want to perform a search. We want to search for everybody that's between Miller and White. And our dictionary is sorted, so we can perform binary search now. One binary search for the start and one for the end. This has to be done inside of a trusted environment, SGX in our case, because the values have to be encrypted, obviously, to see in the binary search if you have to go up or down. So we first search for Miller, we get the value ID of 2, and we search for White and get 4. So 2 binary searches. And we now know that our results are from value ID 2 to 4. And now we keep track of this range and do a linear scan of the attribute vector. So we go from value to value and see if it's between 2 or 4. We do that, and those are the results. Keep in mind, it's now an integer comparison, which is really fast. That's the first thing. And second, this is highly parallelizable. It's a simple check. You can do that on multiple CPUs without any problem. The features of ED1 now. The search is very efficient. We have a dictionary search that's logarithmic and a linear scan of the attribute vector. However, we have full order leakage in the dictionary. What does that mean? That means an attacker knows that this is the smallest value lexicographically, this is the last, and all are in between are sorted. He doesn't know the values, but he knows that they are sorted. OK, let's go to ED2, frequency revealing and wrapped. We want to perform the same search. And now let's think for a moment, OK, let's just do a binary search. A binary search always starts in the middle. So we know the wrapping is at 2. So at least the secure environment knows it's at 2. Yeah, OK, then let's start in the middle. Let's start at Miller, right, which is the middle of an array starting here and going to here. However, you would directly leak where your wrapping is. So you should obviously not do that, because then you can just leave it in the first place. You can stick with ED1 if you directly leak where the wrapping is, because the wrapping is secret and it's different on each column. So we have to perform something else, and we perform a special binary search. I don't go into too much details here, but the key is to encode values that you access on the fly. I presented you here the encoded values. So Smith becomes all zeros. Miller becomes 889, whatever, and all others also are encoded somehow. And the important thing is, look at them, they are sorted. And that's key. So we perform binary search on those encoded values now. And for that, we also encode the start and the end of the range. So we search for Miller 889 and so on, White 394. Perform again 2 of those special binary searches, and those are the results. Which means we have now keep track of 2 result ranges, the range 0, 1 and the range 4, 4 in this example. We again perform an attribute vector search. For every value we look if they fall in between those 2 ranges. And those are the results. Again, remember, the numbers are different. The selected cells are equal. The features of this encrypted dictionary. The search is, again, very efficient. Logarithmic search, linear scan in the attribute vector. The only change is this encoding on the fly. And we will learn in the end how much this costs. The good feature here is the order leakage is bounded now. The attacker does not know anymore where the smallest and biggest values is. He only knows for that with a high probability the value that's next is higher lexicographically, which is only not true for one place. but he does not know at which place this is. OK, to ED3, unsorted, frequency revealing still. We want to perform the same search. We cannot do binary search now, because the dictionary is not sorted anymore. So we have to do a linear scan. We have to linearly look at every value and look if it falls into the range. And those are the results, and we keep track of them. It's important here that the result now is a set. It's not longer a range. It's a set 0, 1, and 3, which means for the attribute vector scan now, we have to look at every value and compare them to every value in the result set from the dictionary search. So for the first, is it 0, 1, 3, 0, 1, 3, 0, 1, 3, and so on. This takes considerably longer than the binary search, than the linear scan with just range comparisons before. So our search is slower. We have a linear dictionary scan, and we have this attribute vector scan that now depends on the number of results of the dictionary scan. However, we don't have any order leakage anymore. The attacker does not know the order of the values in the dictionary. OK. Now I told you everything I want to tell you about those encrypted dictionary, and now let's see how we use them to get a whole database. Here we see we have a data owner, we have some proxy and an application. They are all trusted. So that's very important here. I forgot to mention this in the beginning. We only talk about an encrypted database in this talk. We don't talk about encryption of the applications. My research department, or the research department I work in, we also work on solutions for encrypted applications. But here, only encrypted databases. Sorry. On the right side, we have a cloud provider with a database management server, and he provides an Intel SGX enclave. The first step is now that the data owner generates a key. He then shares the secret key with the enclave. And in this step, he uses the remote attestation that I explained in the beginning. So he makes sure that the enclave is what was promised and that it's running on Intel SGX CPU. He establishes this authenticated channel, which is encrypted end-to-end from the user to the enclave, and only over this channel he will transfer the key. So the key is now inside of the enclave at the database, at the cloud provider, but the cloud provider never learned it. He also shares the secret key with the proxy that's in his trusted environment. It doesn't really matter how that's done. And then he encrypts his data, which means he encrypts his dictionaries. And then he provisions those encrypted dictionaries together with the attribute vectors to the cloud provider. The data is loaded to disk. All data is obviously loaded to disk, and some, or most of it, or all, is loaded into the RAM. This is more or less a setup phase. Then an application sends a query, and this query is sent to the proxy. The proxy will encrypt this query. This does, however, not mean that he just takes the SQL string and encrypt it. It means he will encrypt the values that are in there. So for example, we have a range query. Give me everybody between 20 and 50. Then 20 and 50, those are encrypted, because those are the sensitive values that we consider, not the whole string. The string or the query with those encrypted values is then transferred over to the database management server. You should obviously also use something like TLS to protect this during your network transfer, but this is not really important for us now. At the database management server, then a query pipeline starts. That depends on the database management system you use. For example, some query parsing is happening, query decompositioning is happening. A query optimizer does some things. For example, it loads all the data that's required for the query from disk to the RAM. And then the query goes to the query evaluation engine that then starts the query processing per column. And per column, we have to do two steps. We learned that at the beginning: dictionary search, attribute vector search. And the dictionary search is done inside the enclave, because the enclave has the key, so it can decrypt the values that are inside the query. It will load all data from the RAM that's necessary, also all the dictionary data, to do the processing. This means a linear scan for ED3 or some others, or those binary searches for ED1 and 2. It does this dictionary search and returns value IDs. Value IDs in plain text. And now the query evaluation engine can do the attribute vector search, because this is not sensitive data. And I just want to stay here for a second, because have a look at the enclave. I told you at the beginning, keep the enclave small, and that's what we do here. We did not pack the whole database management system in there. We pack one important functionality in there, and that's it. Still, every data is encrypted at all time. The query evaluation engine then passes back the record IDs to a result renderer. The result renderer will, for example, do tuple reconstruction, join some results, and return the encrypted values back to the proxy. The proxy has the key, decrypts the results, and it's done. This is the whole flow of the database management system. One other important fact here is we encrypt the dictionary. I told this before. This means, in detail, we encrypt every value individually of the dictionary, value by value. This is important so we can perform this binary search or linear scan, right? Because we have to load individual values in. And this is also key so that we can support large, maybe more or less arbitrary large databases with this solution. Because per column, we only have to load one value at a time inside the enclave. We load one value, do binary search, up or down, okay, up or down, next value, decrypted, up or down, and so on. So we by far don't need the 96 megabyte. In our case, we also at the moment use AES GCM, so a hardware-supported encryption scheme, which is really, really fast. Okay. So I told you this before. We have in-memory database, column orientation, dictionary encoding. It's more or less HANA. So let's just put SGX protection in HANA. Let's put encrypted dictionaries in HANA, and we are done. Like that would be my dream. Unfortunately, as I told you at the beginning, I am from research. We did not have the capacity to build it into HANA directly. But here comes one thing you can do for me. If you like what you heard here, please contact whoever you know to build this in. We from research, we want to build it in. So if you are a customer, wants to have it, do it. If you're from SAP, let's do it. We from research, we then build it into a database that's called MoniDB. Most certainly, you never heard of it before, but it's an open source database that came from academia and that has the same features of the top 3. So we built it in there, and so the features are equal to HANA, but it's not HANA. And the evaluation that comes now is then obviously done for MoniDB. And I start with an evaluation of ED1, the frequency revealing and sorted option. And the setup is the following. We have one test column that has almost 11 million entries. Of those 11 million, only slightly more than 13,000 are unique. We analyzed a whole lot of real database columns, and this is a typical scenario, to have only few unique values. On this column, we performed 500 random queries with range sizes 2 and 100. So what does this mean, range size 2 and 100? Please concentrate on me for a second. We have this 13,000 values column. We remove everything that's not unique, every duplicate. It becomes smaller, so 13,000 of them. Then we sort this 13,000 values, and now we pick one of them randomly, and the next. This means a range size of 2. So we search for values that are definitely in there, and that they are consecutively in a sorted list. 100 means more or less the same, random value. 100 later, this is the range we search for. And look at the graph on the right, please, for a second. On the x-axis, we have the database, number of database records from 100,000 to our almost 11 million. And here we see how much values we get back for the range sizes 2 and 100. Because the range size of 2 means we search for 2 consecutive values that are in there. So 2 of the dictionary. But in the attribute vector, they can be multiple times. And you see that here. Even if you have only 100,000 values, we will return 1,000 for a range size of 2. This will become important later. And for a range size of 100, we have even above 10,000 values which are returned. Okay, now to the actual evaluation results. In blue, you see the results of MoneyDB. In green, you see the results of EncDBDB. So what I presented you before. And in purple, which is almost not visible, which it's directly below the green, this is what we call plain DBD. Plain DBDB is a version of EncDBDB, but without encryption. So every values are plain text, we don't use an enclave. Okay, what do we learn from this graph here? First, we are considerably faster than MoneyDB. But that comparison might not be real fair. MoneyDB, they have a lot of functionalities that we don't have in our prototype. They're optimized for different things. But it gives you an idea of where our results lie. That's why I presented to you here. And the second and really important thing is, look at the difference between encryption and not encryption. You cannot even see, basically can't see it. The difference is half a millisecond, more or less on average. For ED1, that's important. We see it ED1 results here. Let's go to ED2. For ED2, I don't. Can we wait for it's like at the end? Okay. For ED2, I don't even show you the results because you would not notice a difference. The difference is so small, it's more or less only 2 milliseconds that we use for this encoding step. So we have additional security, but not much performance loss, which makes it a good idea to use ED2. Let's look at ED3. And the picture changes here a little bit. And it should be clear from what I explained before about ED3. We have those slower searches, linear dictionary search, linear and slower linear search of the attribute vector. And here, the range, so I just go back for a second before, and the results of ED2 and 100, they are almost the same. The y-axis is almost the same, and most certainly you can't see a difference. But for ED3, the difference now is large. The y-axis is 20 here, 100 here. And this is the result of this slower attribute vector search. At the top, 2 values are returned from the dictionary search. At the bottom, 100. This means we have to compare every of those 11 million values, we have to compare them 100 times compared to 2 times. And this is the result of that. But still, you see the difference of encryption is not that high. And that's all I want to tell you about the evaluation today. Key takeaways. I presented to you EncDBDB with its main building block, the encrypted dictionaries. Those 9 encrypted dictionaries present different trade-offs regarding security, storage efficiency, and search efficiency. In Las Vegas, I was asked, which should I use? I don't want to decide for every column which I want to use. And yeah, I'm a researcher, so I would say, yeah, do it. But yeah, obviously that's not a solution. So I would suggest, if you want to have the best security you can get, you have to go for ED9. But in most cases, this is not what you should or might want to do. So go for ED5. ED5 has bounded order leakage, bounded frequency leakage, but the performance loss is really insignificant. So this is most certainly a good choice. The second point of the key takeaways, we from research, we integrated it into an open source data management system. And this database management system, it still supports all the auxiliary database functions. So if your query pipeline, query optimizations, all of that, you can still use that. We only extracted this little point, this dictionary search, put it into the enclave. That's it. And third, we only have a minor performance overhead for our column with 11 million values. It's 5.77 millisecond against 6.45. It's not free, but it's almost free, I would say. It's no security against encryption. And this ends the main part of my talk. I'll just say a few words of this remaining slides here. Of this talk, you unfortunately cannot learn anything about in OpenHAB, at OpenSAP. You can only learn more about this in a paper, or if you can come to me. You can come to me in the end of this talk. I will have also a meetup in half an hour or an hour. You could come there, let's discuss it. You can write me at any point, come to me. You can get a contact card after this talk. Just come to me and let's discuss it. And here, one other thing I want to mention is especially SEC 302. It's enabling privacy-preserving enterprise application. That's done by a colleague of mine in half an hour. You should look at that. Great stuff that we do from research. And another thing is the SAP Security Research Strategy. You can learn there more about all we do from research. I'll just wait a second for that man to make a picture, because it's important, right? And with that, I have time for questions. We have 12 minutes left.
In your graphic, all the dictionaries were encrypted, but I suppose you could also have some of the dictionaries encrypted and some unencrypted. For example, if you had, let's say, one of the columns had no duplicates, but was also not privacy relevant.
Yes, definitely. So we have those 9 encrypted dictionaries, and I talked about this plain DBD for a second, right? You can consider them more or less as 9 additional dictionaries, plain text dictionaries.
Okay.
And our system, it can at the moment, this MongoDB implementation, it can support all of those 18 variants at the same time. Yes.
What about the join performance on the one hand, and on the other hand, the aggregation of data?
Yes. We did not at all look at that for now. It's, as said, a research project at the moment. It's I do my PhD at SAP currently. This was one task of that. And we don't know. For joins, it's tricky, let's say. I didn't think much about that. But aggregates are not. Aggregates are simple and fast. Right? So at least if you, let's say, give me a sum of all ages, might not make much sense, but that's pretty fast. Linear access, one sum in the enclave, go through it, done. We, for example, compared it to homomorphic encryption, if you know what that is. It's like a specific encryption where you have encrypted values and you, let's say, multiplicate values next to each other, onto each other, and in the end you have an encrypted result. Compared to that, an SGX version is 10 times faster. So it's, if I remember correctly, it was plain text was 0.8 milliseconds compared to so plain text 0.8, encrypted 1.2. So yeah, at least again overhead, but really minor.
But this implicates that the function must be implemented in the secure enclave. Otherwise, you leak data.
Yes. Yeah. But for example, let's say the sum or average or whatever, this is again one small functionality, right? It's pretty easy. It's 10 lines of code, which I would consider small, and which you can keep free of side channel leakages and so on.
So you were talking about how the values are encrypted in the dictionary. And you stated that for 2 equal values, you would get 2 different encryption results, correct?
Yes.
Where is the information stored to retrieve the original value? So you would need more than just one key to restore both values then, wouldn't you?
Almost. In, for example, ASGCM, which we used, you use key and an initialization vector. Right? And so you have your key and your initialization vector, which is purely random. And this is key, right? You have two equal values, two different initialization vectors, which means the ciphertext will be different. And in the ciphertext, so to the ciphertext, you just add the initialization vector. Adds a little bit storage overhead, but that's minor. It's, if I remember correctly, so we don't only have this, we also used integrity protection. And those two features, integrity protection and this randomization, it's about 25 byte per value. So it's also not free, but it depends on how long your value is. That's what you have, yes. So it's more or less a second key.
Okay, so if you wanted to join on values, wouldn't you have to keep track of those initialization vectors so you can actually compare values at that point?
As told, the initialization vectors, they are stored directly with the ciphertext. So yes, we keep track of them. But you load the value from main memory inside the enclave. You just take the value, call some SGX SDK, and it will return you the plaintext value. Right? Then you have the plaintext value, and then you can see are two plaintext values the same? Then yes, join them.
But the dictionary has to be created on the client side, correct?
So that's at least what we do in our research project, because for researchers it's always very, very, very important to exactly be able to define the leakage. But like in a real scenario, that's obviously not necessary. Right? You would just call an insert SQL, the proxy would encrypt it, the enclave would decrypt it first, see where it fits, does a dictionary search, see where it fits, and inserts it. So it's also possible to do it dynamically, but it's not done in our prototype now. So if there are no other questions, so colleagues from SAP, contact other colleagues, let's build it in. Customers, contact your guys at SAP, we want to build it in. Freelancer, maybe you can help us build it in. Okay, and with that, thank you very much.